Welcome to This Explainer. We're diving straight into the fascinating and honestly mind-bending evolution of how artificial intelligence is processing both images and text to become active, autonomous digital agents. If you follow the AI space, you already know things are moving at absolute lightning speed. But today, we are getting under the hood to break down exactly how these systems actually work.
Here is our agenda for today. 1. Seeing the digital world. 2. Clash of the architectures. 3. The benchmark scoreboard. 4. Optimizing for the edge. And 5. The agentic horizon.
Section 1. Seeing the digital world, the AI paradigm shift.
So, how do modern AI models actually see the world? It's a profound question, right? Because AI models aren't just reading text anymore. They're looking at incredibly complex visual data and making sense of it simultaneously. We are way past basic image tagging at this point.
You see, instead of the clunky old method of loosely combining a discrete vision system over here and a text system over there, today's vision language models, or VLMs, process complex tasks in one seamless unified network. This shared representation space is absolutely critical. It's what allows an AI to do things that require simultaneous spatial reasoning and language generation, like deeply analyzing the layout of a complex financial document, or having a fluid, multi-turn dialogue with you about a photograph.
Section 2, Clash of the Architectures, the architectural bake-off. What's really fascinating here is that these models represent completely different philosophies of visual processing. Take Alibaba Cloud's QN 2.5 VL. It uses something called dynamic resolution. Think of QN as looking at the raw, original canvas. It preserves the native aspect ratio so it doesn't discard any of those fine-grained visual details. Now contrast that with Meta's Llama, which uses fixed grid tiling. Llama essentially chops a photograph into uniform puzzle pieces, these padded grids, and then feeds those pieces into the pre-trained Llama 3.1 text model. Two very different ways to solve the exact same problem. But, complex architecture isn't the only way to win this game. Models like Florence-2 and the Allen Institute's Molmo prove that highly curated data can be just as powerful as fancy mechanics. Florence-2 treats literally every single computer vision task as a text generation problem, and it pulls that off thanks to a massive dataset with 5.4 billion annotations. Molmo goes a different route. It intentionally uses a simpler architecture but feeds it this hyper-curated 1 million paired dataset called PixMo. And then you have highly specialized models like PointsReader, which streamlines the whole process using a two-stage data strategy specifically for rapid document conversion.
Section 3. The benchmark scoreboard, the quantitative bake-off.
So, the ultimate question. How do these different architectural philosophies actually stack up in the real world? Well, Quen's dynamic resolution absolutely dominates document parsing. It hits a massive 96.4% on DocVQA, which is a brutally hard visual question-answering benchmark for documents. But check out Molmo. Despite only having 7 billion parameters, its curated training data lets it hit 77.3% on the massive multidiscipline MMU benchmark. It is literally punching way above its weight class, going toe-to-toe with giant proprietary models.
Looking at these trends, a few things become crystal clear. Dynamic resolution is just vastly superior at preserving spatial relationships. If you're dealing with multi-oriented or handwritten text, fixed grids tend to awkwardly split tiny text across their artificial boundaries, which ruins comprehension. We also see that highly curated datasets are the great equalizer for smaller models. However, mathematical and scientific reasoning, like on the MathVista benchmark, is still a massive bottleneck. Why? Because succeeding there isn't just about seeing the image perfectly, it requires multi-step logical reasoning. And that is heavily constrained by the raw parameter size of the underlying language model.
Section 4. Optimizing for the edge, fitting massive models on GPUs. Let's bring this down to earth. How do you actually fit these massive models onto your consumer-grade hardware at home? Deploying them locally requires a simple but incredibly strict pipeline. You load the model directly via Hugging Face, sure, but the magic and the danger zone is in step 2, pre-processing. Strict memory management is absolutely critical here. For instance, you have to explicitly set pixel boundaries, resizing images so their dimensions round to the nearest multiple of 28. This preserves consistency with a model's internal patch size and keeps your GPU from instantly running out of memory. Now throw video into the mix, and things get wildly tricky. Video analysis treats temporal data as a series of sequential images, meaning your memory usage scales exponentially with the video's length and frame rate. If you don't strategically configure specific frame rate constraints and sample the frames to reduce temporal redundancy, you will crash your hardware in seconds. But this is where it gets fun. The sheer scale of optimization available today is phenomenal. Low-bit quantization allows massive models to run smoothly on standard hardware. Look closely at 4-bit quantization. It reduces your GPU VRAM requirement by a massive 72%, and get this, you sacrifice less than 3.5% in visual accuracy. A 72% memory reduction for a tiny accuracy drop? That is literally a game changer for local edge deployment.
And if you need to squeeze out even more efficiency, formats like GGUF offer dynamic quantization. Think of it like a really smart budget manager for your GPU. It spends your high precision, like 8-bit memory, only on the layers that desperately need it, like critical embeddings. Meanwhile, it saves memory by assigning lower 2-bit or 4-bit precision to the intermediate attention layers. It's incredibly clever.
Section 5, the Agentic Horizon, from passive to active.
All of that optimization we just talked about, it builds toward the ultimate payoff. We're literally witnessing a massive evolutionary leap right now. We are moving away from models that just passively describe a static image to active models that can take real-world action based on what they see in real time.
Because these newer models can output highly precise spatial coordinates like exact bounding boxes or specific UI points formatted flawlessly in JSON, they can interface directly with standard automation tools. By combining a model like Qwen or Gemini with something like Playwright or Google's Computer Use API, the AI can literally take over your mouse and keyboard. It simulates human clicks and keystrokes to navigate user interfaces, autonomously completing tedious data entry in finance or running complex software tests. The major takeaway here is that these models are rapidly becoming active digital assistants, living natively inside your operating system. It's all about this cohesive foundation, seeing the screen perfectly, reasoning about what's there using language, and autonomously executing the right tool to get the job done. So I'll leave you with this provocative thought. As the barrier between human interfaces and AI cognition completely dissolves, what limits are actually left on what we can automate? The tools are now in your hands, fully optimized and running on your own hardware. What will you build?